Okay, I'm going to talk about how numbers are represented inside the Java virtual machine and inside the programming language itself. And there are different ways in which we represent numbers. We've already talked about the integer representation, and there are several other ways that numbers are represented. They're called data types, or primitive data types. And with that um, as a bit of a clue what we're talking about, let's talk about some of these data types. And Java has a pretty nice collection of data types, and a smart programmer can use the differences between data types to do things in the program itself. Okay, the smallest or simplest, the one that requires the least amount of memory, is called the byte. Okay, the byte. The byte is an 8-bit signed 2's complement integer. Okay, 8-bit. Now we know that 8-bit numbers, we remember from our discussion of binary representations of numbers, that an 8-bit, with 8 bits, we can represent 2 to the 8th different numbers, and 2 to the 8th is 256. 2's complement is a way in which the numbers are represented in the computer itself. Now, I would have said the hardware representation of the numbers, but in Java, what we actually have is a virtual computer, a computer that exists in software inside your computer. It's called the Java virtual machine. So in Java, it's not actually a hardware representation. We'll call it the architecture of how numbers are represented. Now, and I'll explain that briefly in a moment, what a 2's complement number looks like inside a computer. But in Java, the numbers will go from negative 128 to 128. And if you count that up, you'll see that those are 256 different values. And that is the byte representation. Then, up from that, there's what's called the short representation. And consider a short as being a version of the integer representation. The short representation represents a number, represents using a 16-bit signed 2's complement integer. Okay, remember 16-bit numbers can represent 2 to the 16th different values. Okay, and those values will range from negative 32,768 to positive 32,767 inclusive. Okay, so those are our 16-bit short integers. So the short is an integer representation, and it represents more values than the byte. Now, the reason why we have these representations is because if we have large arrays of numbers and we use let's say, the byte to represent the numbers, it takes up less memory in the computer than does the short, okay, by quite a bit. So if all of our numbers can fit in the range between negative 128 to 127, we might want to use the byte representation to use less memory. The short uses quite a bit more memory, but nevertheless, the short uses less memory than the integer representation. When we're already familiar with the integer representation, it uses a 32-bit signed 2's complement integer. So it's 2 to the 32 different numbers can be represented in an integer value, and that goes from negative 2 billion blah 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 up to 2 billion blah 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 inclusive. So that's a lot more numeric values than can be represented by the short or the byte. Okay, so and then finally the next way of representing an integer value is with the long. The long is a 64-bit signed 2's complement integer, and that goes from a really big negative number to a really positive negative number. Okay, so that takes up a lot of memory. Okay, after that, so these are what's called, these are integer variables right in here. Byte, short, int, and long. Now we go into some other types. There's a floating point number. A floating point number is a 32-bit, okay, IEEE 754 floating point. I won't go into the explanation of what that is if you'll give me that break here. And it is a way of representing numbers that are fractions. Okay, because the previous numbers, the long, the integer, the byte, and the short, only represent numbers that are whole numbers. Okay, so float gives us a way of representing numbers that are fractions, and in particular decimals. And then we have a large, so this is a 32-bit number. Okay, so 32-bit number can still represent only 2 to the 32 different values, except it allows us to do fractions. The double allows us to represent a larger set of numbers. It's a 64-bit number, and again, it still allows us to represent fractions. Another useful data type is called the Boolean, and the Boolean only takes on values of true and false. Only takes on 2 values. So if you like, a Boolean is can represent it just by only a single bit, 1 bit. It's either on or off, 0, 1, true, or false. And then the final way of representing numbers in the computer is with the character, and we're familiar with character strings from the basic programming language, for instance. And character strings are kind of like integers, except we use them, they're 16-bit, and it's what's called a Unicode character. And a Unicode is a generalization of the ASCII code, and we've used the ASCII code before. And Unicode, where the ASCII code is a subset of the Unicode, and that all of the ASCII characters are included in Unicode, and they have the same numeric representation. So, for example, the ASCII character 32 is a blank space, and it's also a blank space in Unicode. And so when we represent, typically, character is used to represent strings of characters, alphabet, and so on. And the Unicode allows us to represent characters in multiple languages in addition to the ASCII characters. Okay, so that is a brief introduction into our character types. One other thing I wanted to mention is 2's complement. And 2's complement is a way of representing numbers, as I said, in the computer. And so, for example, here I have the 2's complement value of 0 is represented by a set of, if you like, transistors or in the hardware of the computer. The 0, 0, 0, all these binary digits are set to 0, and it's the 2's complement value of 0. 2's complement value of 1 is this, so it's what we would expect it. 2's complement value of 2 is this. Okay, 126 is this. 127 is this. So you see, this is representing what we expect it to. However, in 2's complement, we have a way of representing positive and negative numbers. And all the positive numbers, this last term, this leading term here is always a 0. For negative numbers, that leading term is always a 1. So negative 128 is represented as 1 followed by all these zeros. Negative 127 is a 1 followed by that with a 1 there, and so on. So a negative 254, 1, 1, 1, 1, 1, 0. I'm sorry, this is a negative 2. The unsigned value would be 250. This is a negative 2 right here, and a negative 1 is this number right in here. So interestingly here, you see the difference between, for example, a negative 1 here and the plus 1 here. So the 2's complement is a way that the numbers are represented inside the computer. And then your arithmetic operations in 2's complement are designed to work with this way of representing numbers. So for example, if we were to take a 1 and add it to a -1 in 2's complement, the answer would be a 0, would be this. So I'll leave that there. I'm not going to talk a little bit anymore about 2's complement right now, but you can see this is an interesting property of computers and how the computers represent their numbers. Okay, now let's talk some about Java programming. Okay, now here is the computer program that I want to talk about right now in this video. Now, it's a representation of data types, and in particular what I want to show is the difference between the integer data type and the double data type. Because the double is one of the most commonly used ways of representing the floating point numbers. Okay, we typically don't represent it using the float variable. We use it representing the double variable. And the reason is because many of the common Java programs that we incorporate in the programs that we write. So we call these canned pre-written Java programs, and these Java programs have been themselves written to use the double data representation. So we use the double so that when we call them, we're consistent. So we want to talk about the difference between the integer and the double representation. So here is the program right here. I have it. I want you to pause the video and type this into your Dr. Java. And I've already done that. And we want to type it carefully. And with some luck, we can type it so that we won't make any typing mistakes and that the program will, in fact, compile. So I typed it in here, and I actually tried to compile it and run it, and lo and behold, I did something rare for me in that I typed it, and it compiled the first time. Okay, so we're going to call this program, or this class, which is the Java way of name for a program, call this class example3. So this is the program example3. And as we have done in the previous examples, the first thing we do is we put in the public static void main statement. And then we enclose this in parentheses, a parentheses here and a parentheses here. We say string args and then an open bracket and a closed bracket. So we need to have this string args statement inside the public static void in order for the program to run properly. We do an open bracket here. Okay, and then I declare the variable var to be an integer variable. And I end it with a semicolon because that's the termination of that executable statement. And then I have my comment that tells what that statement is. Now recall that a // is a way of putting a comment on a single line, and recall that the /* is a way of beginning a block comment. Everything between the /* and the / is considered itself to be a comment. Everything from here to here is viewed as being a comment. So we set we declare the variable var to be an integer variable. Here we declare the variable x to be a double variable. So this will represent a fractional value, a decimal value, and we're making it a double or double precision variable. Again, we put a semicolon to end the statement, and then again we have a // and a comment. So we declare it as a floating point variable. Then I do the initial assignment. I say variable equals 10, again semicolon and a comment, and I say x equals 10. But notice I've written x as being 10.0. Okay, and I've done that because I can. I could have said x equal to 10 just like I did with variable. But variable, I could not have written this as equal to 10.0, or I would have automatically just set it back to 10. So this is to indicate for you and me that this is in fact a floating point variable. Then the next thing I'm going to do is I'm going to print out the values for variable and x. And I do that with the system.out.print statement, and I do the print ln. So it does a return after it prints the line out. So it prints the line, and then it automatically skips to the next line to continue with the following with the any more print statements that we might have in there. So we print original value of variable colon, okay, and this is all put in quotation marks, and then plus, this is telling the print statement that we want to print something else in addition to what we have in the character string, when what we want the else is we want to print the value of the variable var. So it should print this. Then we do another system out, print line. So on the next line it prints this, and then here it's printing out the value of x, and then it skips another line. And then we do a system out print line, and there's nothing in here, so it's just printing a blank line. Okay, now I'm going to take the variables var, and the variable x and divide both by 4. So I set var equal to var divided by 4, and I set x equal to x divided by 4. And we played around with this a little bit last time. For the integer variable, when I take it and divide it by 4, whatever value you would get by taking variable and dividing it by 4, it truncates that to an integer value. So if we took var divided by 4 and we have some decimal when we do that division, it just drops the decimal component and only gives us the integer component, the integer part of the answer of doing this division. On the other hand, x, being a double precision floating point a number, a decimal number, a fractional number, includes the decimal values. So now I do another system out print, and I print the value variable, and I print the value of x. So we can see what happens when we divide the original numbers by 4, original number integer 10 by 4, and the double precision floating point number x equal to 10, divide that by 4. So we can compile our program, okay, and like I said, I typed it in very carefully and it compiled for me the first time. So we compile it and then run, and here's the answer that I get. Okay, running it, what I get is first it prints out 10 and 10.0, which are the values that we set for var and x. And then after we divide by 4, a variable, the integer variable, division by 4, we do 10 divided by 4 is 2 plus a fraction, 2.5, but it only gives us the integer part of that division and puts that into variable. So this is the integer calculation of 10 divided by 4 equal 2.5, but it drops the half and gives us the 2. And here's the real number, the double precision floating point real number. Divide x by 4, and it gives us the whole correct answer, 2.5, and it includes in that the fractional part. So that is my discussion of the variable types that appear in Java. So until next time.